Okay, here we go with my big idea that I'm trying to get across. This torturous method of learning instantaneous rate of change, I stole this right from advanced functions, a completed version of this note. You don't have to copy anything. Just try to remember what we were doing to do instantaneous rate of change. We'd find the average rate of change between 1 and 2 seconds and say, okay, the instantaneous rate of change is close to 10.3 because the average rate of change from 1 to 2 is 10.3. And this must be close to the answer. But as we found out later, it's not that close to the answer. It is close. And then we went, oh, we'll get a better answer if we go 1 to 1.5. A better answer was 12.75. Do you remember this? It was torture, and it's on purpose. I got to tell you, the curriculum's been designed by decades of mathematicians going, what's the best thing to do here? And the best thing to do here was torture you so that what I'm going to explain next is perfectly clear. Yeah? So then you get closer and closer, and eventually you see, as you get closer, and this is the big moment of this explanation, as I got closer to 1, see it was 1 to 2, and that wasn't that close. 1 to 1.5, that wasn't that close. But as I got closer and closer to 1, the average rate of change got closer and closer to the instantaneous rate of change. How close did it get? The answer is as close as you want it to get. We can get as good an answer as you want here. We decided the answer was 15.2. By building this table, we can go 15.199, 1999, 1999. We can get as close as you want to 15.2, past any error that you want to put in there and say, well, we've got to get in within thousands here. No problem. I just got to keep going. Well, I want to get within millions here. No problem. I just have to keep going. So it's as close as you want. So by getting this really close, we can get this answer really close. That was the big idea there. And what that's called, and it's a word I didn't use there, it's called the limit. We know what the limit is here. The limit here is 15.2. That's what it's heading towards. That's the new word here, is limit. What is it going to head towards? And the applications are unbelievable. It is not exaggerating to say that when Newton and his buddies, I say buddies because they were not buddies, they hated each other back then. Isaac Newton and his buddies came up with calculus. This was the breakthrough. There was math they could not do. And then when limits came along, which I'm going to show you today, all of a sudden there was math that seemed impossible before that they could do pretty easily. And it's not exaggerating to say, and then the world changed. We went thousands of years, and the best we could do was brick castles and bow and arrow. Thousands of years. That was the big accomplishments in the world. Calculus came along, and suddenly cars, skyscrapers, airplanes, iPhones, internet, satellite, traveling to the moon all became possible because we could do the math. And it sounds like I'm exaggerating for effect as a math teacher, and I'm not. What you're about to see gives you the power to do everything that happened in the last couple of centuries, and especially this century. Einstein came along and took this all to a new level and said, hey, I can take this math and do stuff with it that no one ever thought of before. You know? So it's been a great century that way, and the breakthroughs are still happening. Not as fast, though. The breakthroughs are slowing down. It's harder to learn everything that's available and make a breakthrough now because there's so much to learn. Okay, back on track. The actual lesson. Here's the definition of a limit of a function. And it's a little slippery. It takes a little while. But every time you're wondering about what a limit truly is, you can think back of what we did in those tables in advanced functions. What are we headed towards? What are we headed towards? Okay. So the limit of a function, we got a new notation here. It'll say lim instead of limit. Not the greatest short form in history, I got to tell you. You know, saved us 2 whole letters. But it's iconic. It's the ultimate symbol in mathematics, I got to tell you. Limit as x approaches a. This x is saying where is the x going towards? So this says x goes towards a. Back to my other table. Here, x was heading towards 1. You know, we had our value that was heading towards something. And then equals L means we found the limit. And then the example was 15.2. So we head x towards something. We got something we're working on. And we get an answer out of that. On a scale of 1 to 10, the big idea should be like an 8 now. It's like, okay, we're heading towards something. And the symbol should be like a 3 now. You're like, I sort of. You know, and so this lesson's all about just using this symbol and getting used to what this symbol does. How do you read it? It says the limit of f at x as x approaches a is L. You see I can barely stand still here. My feet are moving back and forth. So wound up about limits. It's unbelievable what's going to happen in the next 2 chapters. By the end of the next 2 chapters, it's like as much progress as you've made in math the last 3 years, we'll do that in 2 weeks now. You know what I mean? Like it's unbelievable what we're going to be able to do now. Okay, now just to get into the details. As x approaches a from both sides, you ran into that in advanced functions too. I didn't really force it on you because I knew it wasn't a big deal at the time. We just came at 1 from above. We go at 2, 1.5, 1.1, 1.01, 1.001. It was enough to come from one side. And for many functions, it is enough to come from one side because you'll get the same answer from the other side. And I forced you to a couple times to do it from both sides. Where was it? You know, so we came here, we came at 1 from the right, and we came at 1 from the left. And I forced you to do it just so you saw that sometimes you have to come from both sides. But it wasn't really a big deal at that time. But we'd say now, we want to make a big deal about it, that it's got to do it from, it's got to approach it from both sides. You'll see more of that now. This definition is very specific. To obtain the limit, okay, here we go. To obtain the limit, we need to approach the a value from both sides. That might be a little mysterious, but that's a big idea I need to get to during this lesson. In my 50-minute time limit, I put on this. To see why it is so important to approach the a value from both sides when finding a limit, consider the following example. Take a look at this. Find the limit as x approaches 0 of f at x from the graph below. Now, basically, everything I'm about to say right now is written there, so you really don't have to write anything down. That's on purpose. I don't want you to be scrambling to write things down while I'm explaining this, because I'll read this when I'm done, but I think I'm going to say everything that's on the bottom of the screen now. What we mean by as limit as x approaches 0 of f at x is, here's the function f at x, and we're going to make our x values get closer and closer to 0 and see what the function does. Okay? So, I'm not going to be really close to 0. I've got to get really close to 0, but I'm not going to start there. I'm going to start here and say, oh, over here, x is really small. It's like, like 0.1. Oh, now it's like, 0.2. I'm getting closer and closer to 0. I'm on my way. Oh, it's like 0.5 now. Oh, now it's like 0.7. Oh, it's almost 1 now. Oh, it's 2. Oh, it's 4. You see, I'm getting closer and closer to 0. Now it's 8. Now it's 15. It just goes up, like straight up. It goes right off the screen upwards and just keeps right on going. As you get closer and closer to 0, this function heads to infinity. And it just goes straight up. Okay, so that is a possibility and a limit that what the answer you'll get is infinity. Now, I just got to be a little careful here because that was from the right side. Now I'm going to do something else underneath. I'm going to go, well, what if I come from the left side? As I come from the left side, I go, oh, well, negative 0.5, negative 0.8, negative 2, negative 50, negative 100, negative 1,000. It just goes crazy like that. It heads to negative infinity from that side, and that's a really big difference. In fact, that's as big a difference as you can have, actually. Infinity and negative infinity. Yeah, those are big differences. Like, oh, you just forgot the negative. Oh, yeah? If I offered you infinity money versus negative infinity money, that's a really big deal. Yeah? Just forgetting a negative is a really, really big deal. Yeah? Now, because there's 2 different limits going on here, coming from the right-hand side and from the left-hand side, this limit has another little symbol in there. I put a little plus beside the 0 to say, oh, that was coming in from the right side. And then when I came in from the left side, I put a little negative there. That's the best we came up with. A little L and a little R might have been a better choice, looking back. But plus and minus is what we use. Plus means I'm coming in from the right side. Minus means I'm coming in from the left side. Can you see that the limit is different depending on which side I come in? Here's my hand visualization. See it? It doesn't head towards the same thing as I come from each side. Back in advanced functions, they were all set up to go to the same thing from both sides, so it never went wrong here. Here's one that goes wrong. So actually what we say here then is 3 different limits in one question. From the right side, it goes to positive infinity. From the left side, it goes to negative infinity. So the actual limit, not right or left, does not exist. there isn't one specific limit that this thing heads towards. And I'm going to do a bunch where it does head towards something, so you can go, okay, well, how does this work when it does head towards something? And this is just the opening example to show off that coming from the left and coming from the right and comparing the two matters. So this question has 3 different limits. From the right, the answer exists, positive infinity. From the left, it exists, negative infinity. Overall, though, they're not heading towards the same thing, so there isn't one limit I can quote as the answer. Some profs, some universities, some textbooks don't like you to say a limit approaches infinity. We know what we mean by that, but they don't like that terminology. They say, well, it can't exist if it's infinity. That's not a number, all right? So in this course, and don't get worried about this right now, and I'm not going to burn you on a test with this, all right? This is just moving forward. I'm going to put, anytime I do an infinity with a limit, I'll put it in little quotes. That gets you ready for both types of profs. Some profs say, when you get infinity, you got to write that doesn't exist. You can't have a limit that goes to infinity. There's no limit there. You just said it was a limit and you just said infinity. I get what those profs are saying completely. Some profs are saying, when we write infinity, we know what we're talking about. We mean it goes off like this. I understand it's not technically a limit, but it's very descriptive of what's going on. So we're going to use it because we like it. I'm like, I like that answer too. Both are very good. So I'll split the difference, getting you ready for both types of profs. Infinity, you know what I mean? Like it's heading off to infinity. You know what I mean? Yeah? All right, good. I think that's what it says all down here. Yeah? So you don't have to really write anything down there necessarily. Any questions on that, though? If the whole big idea is still a little slippery here, that's okay. The rest of the lesson is just, well, let's try this limit. Well, let's try this limit. And just getting to know this symbol a little more and what the answers mean, okay? Formally, this is just in formal words, textbook type language, exactly what I just said. The limit as x approaches a with a little negative means come at it from the left side. Limit as x approaches a with a little positive sign means comes at it from the right side. And a two-sided limit is if both of those answers come out to be the same thing. They have to be heading towards the same thing. Okay? Limits that fail to exist, if those limits don't equal each other, we call that it does not exist. It's a very common phrase in limits to say, oh, this limit doesn't exist. That's everything from the first slide said formally. I'm going to trust you because you've been good about asking me questions. I can't trust some of my grade 9s just yet to do one of two things. One, when they have a question, to ask me. And two, if I go too fast, to slow me down and make me go back to the previous slide. So I'm not going to, every time I end up with a slide, say, any questions? Do you need more time? I'll just keep going, and you'll stop me when you have trouble. We're already on slide 4 of the first half of this lesson. Okay, an easier example here. Same stuff, but easier. Limit as x approaches 2 from the positive side. When I say x approaches 2 with a little plus sign, what do I mean? Come from the right-hand side, the positive version of this. So I'm heading towards x value 2. I'm following along to see where the function's heading. Where is it heading towards as I get close to 2? You sort of need 2 hands to do this. You got to be like, okay, my x's are going along here, so what's the function doing? What number is the function heading towards? Right there, -4. So as I approach 2, from the positive side, I get a value of -4. Notice it doesn't actually get there. See, the closed dot's up there. I'm going to put the open dot in there and say, it doesn't actually get there, and I don't care in limits. Limits is, where is it headed towards? It doesn't have to get there. It just has to head there. Yeah? Well, why is that allowed? Oh, you'll see as we go along. There's some great examples coming up in the next few lessons that go, oh, that's why we only care where it's headed towards. We don't care if it actually gets there. Okay. Limit as x approaches 2 from the negative side. That means come from the left side. As I come in from the left side towards 2, where's the function heading towards? 2. So then what would you say about limit as x approaches 2? Not left side, not right side. It's like the conclusion of the whole thing. What would you say about that limit? It doesn't exist. These two have to come out to the same thing. It's almost like, you're talking to a friend on the phone, and they're driving somewhere, you're driving somewhere, you're both looking at your GPS, and you go, hey, where are you going? I'm going to 2. Yeah, where are you going? Oh, I'm going to -4. they're not going to meet up, so the limit doesn't exist. This meeting is not going to happen. So in the previous two examples, the limit did not exist due to a discontinuity in the graph. At an x value where there's no discontinuity, though, finding the limit is very easy. Like very easy. It's going to be easy to find limits when there's not discontinuities. That's why we care about discontinuities, is because they indicate spots where the limits might not exist. So for a while, life's going to get really easy here. For about 5 or 6 examples in a row, limits are going to become the simplest thing you've seen in a while. And then we'll accelerate into some awesome algebra. Limit as x approaches 2. As you approach 2 from the right side, this function goes to negative 2. As you approach negative 2, as you approach negative 2 from the left side, this function heads towards a y value of negative 2. So the limit as x approaches negative 2 of f at x is negative 2. It heads towards negative 2. So brainwave comes. As long as this thing's continuous, there's nothing weird about limits at all. It's just where it's headed towards. That's all. Done. Limits are easy. No tricks, no jokes, no curveballs when the function is continuous. Yeah, you just go, where is it headed towards? It's headed towards where it is. Yeah, that's only with discontinuities that things get a little weird. Another example, limit as x approaches 4. So there's 4 there. As I head in from the right side, it's heading towards, I can't read the scales, it's got to be 16. This is, yeah, okay. As you head in from the negative side, it's heading towards 16. The limit is 16. Another example, just to really reiterate, if things are continuous, finding the limit is so easy. It's ridiculous that we've come this far to find these kind of limits. And that's good. Don't feel bad about that. Yeah? Questions about those? Last slide of this part of the lesson, and then we get into the good stuff. As seen in the previous two examples, when working with continuous functions, there's often no difference between the limit approaching a certain x value and the function's y value. When the function is more complicated, we can still use this idea. Our plan is just to sub the number in. Yeah? Looking at this one, you're like, I didn't need the graph. I could have just taken 4, subbed it into the function, got 16, and I didn't have to do any of this graphical work. And you're right. Our plan for finding limits will be subbing in all the time. We're just going to sub in numbers to get the answers. And you're like, well, then what's the problem? Oh, wait till you see what the problem is. It's going to be good. Yeah? Note, the terminology limit does not exist is used when the limit cannot be evaluated or if the limit's infinity. When it's infinity, many profs and many textbooks say, no, infinity is also a does not exist. But then you'll see other profs and other textbooks go, no, we can say infinity. We know what we mean when we say infinity. We know it's going off like this, okay? I'm not going to burn you out in either way. I will tiptoe around this problem and not ever ask the question. Or if I do, I'll accept either answer, yeah? I just wanted to say it out loud so you're prepped for that stuff when it comes next year. Oh, that's the end of that. All right. 6 more slides. Oh, yeah, 35 minutes. For once, I'm going to hit my time target. Beautiful. Evaluate each of the following limits. This is what your homework's going to look like. This is the kind of questions you're going to see on tests and so on. This is what you have to be able to do with limits. It says limit as x approaches 8 of 4x cubed plus 1. From what I've taught so far, you're like, okay, so I'm going to have to graph 4x cubed plus 1 and then look at what it does from left and from right and everything and go through all that. No. This is a polynomial, and polynomials are very friendly. They go like this. This is way back to this type of thinking, you know. Polynomials are it might have seemed complicated, but looking back, it was pretty straightforward. You know, you just find out where it hits the graph, where it hits the x-axis, and it just goes up and down like this. And you're not too worried about everything that's going on there. It's not till we did rational functions and started getting vertical asymptotes that things went haywire. Yeah? Sine and cos. Very nice. Yeah? Just sub in, get the answers. And then tan came along and went, yeah? You want to play, huh? All right? So when we can recognize the function, and why all that work in advanced functions went into learning functions, is that we want to be able to look at this and go, oh, it's continuous. And if it's continuous, you can just sub in. So simple. Well, it's simple if you have the knowledge. You need two pieces of knowledge to do these. One is, you need the knowledge that I know if it's continuous, I can just sub in. And two, I know the function well enough to know it's continuous. This doesn't have any vertical asymptotes, doesn't have any holes, nothing. 8 cubed, 64, 512, times 4, 2049. Someone got a calculator there to double check? I'd love to check these just to make sure I'm not getting old. Somewhere along the way, one of those will slip through my fingers, and then it'll be time for me to buy my boat. Did I tell you what I'm going to name my boat when I buy it? Think this over. It's so clever and so funny. The Sea Can't. You think it over. It's good. All right. In the effort to make a sub-question difficult, I put up the number 9 there. Because the number 9, in the middle of all these crazy functions, confuses people. What does the function 9 look like? Y equals 9. It's so easy, it's incredibly hard. Yeah, it's just a function where it's 9 all the time. So I say, okay, well, what's the limit of the function 9 when you approach negative 200? Okay, the function's 9. Then, oh, what if you approach negative 200? Like, the function's 9. It's 9. It's always 9. You're like, I know, but I'm approaching negative 200. Like, I am Groot. Yeah? 9. I'm always 9. Yeah? I am Steve Rogers. Okay, now things start to heat up. There's examples like these. There's plenty of examples like these. And I always put one on the test just to check. I go, here's a crazy function that's continuous. What do you do? And you look and you go, oh, this function's crazy. Oh, it's continuous. Sub in. Done. Yeah? This thing now. Piecewise. Now we have to be a little careful because we don't know if it's continuous. We don't know if 2x minus 1, a line, and x squared minus 5, a parabola, we don't know if they meet up at the x value 3. Notice, if they had asked for limit as x approaches 2, I had nothing to worry about. I can just use this part of the function and sub in. If they had said 5, 5's no problem. There's lots of numbers that would be no problem. There's only one number in the whole sequence, in the whole pile of numbers out there, that might be a problem here. 2x minus 1, that's continuous. X squared minus 5, that's continuous. But do they match up? How do we find out if they do match up? It's so easy. Just sub in 3 to both of them and see what they both do. Yeah? So, limit as x approaches 3 from the negative side, and I'm just going to call this thing f at x, means I sub into the lower part of the function. That side is heading towards 5. Limit as x approaches 3 from the positive side, which means I use the positive side of the function, the greater side of the function, I sub into the quadratic part, the parabola, and now I'm ready. Therefore, limit as x approaches 3 of f at x. What will you just say about that limit now that I've done both the left and right side? Doesn't exist. Now, technically speaking, I've dropped f at x in there just to make it easy to write the answer here. Technically, I probably should have done this beforehand and said, okay, f at x equals 2x minus 1, x less than or equal to 3, x squared minus 5, x greater than 3. I'm not really worried about that little bit of technicality there, but I do want to mention that I started calling this thing f at x, and it was never called f at x when it started. So maybe beforehand I got to say, okay, I'm going to call this thing f at x. Not a big deal, but technically I should have done that. Any questions about that? Oh, I'm going to hit this target in half. More time there? Who needs more time? Maybe I won't be able to stop saying more time. I'm addicted to saying, asking if you need more time. Okay, limit as x approaches 3. The function is 9x when x is less than negative 2. And the other function is x plus 3, x greater than or equal to negative 2. I think I've said enough things to get you ready for how to handle this piecewise question. What do you suggest we do to find this limit? Say it again. He says plug 3 into the lower function. He didn't say plug them into both. Why don't we have to plug them into both this time? Yeah, 3 is only in this domain. If x is greater than or equal to negative 2, we're only using this part. I don't have to sub into both of them. I only have to sub into that one because it's not where these two things meet up. Yeah? So, limit as x approaches 3, I'm going to call this thing of g at x, is square root of 3 plus 13, root 16, is 4. So you don't have to sub it into both if you're not finding the limit where the rule changes. The rule isn't changing here. If you want, I'll draw a quick sketch of this thing so you can see what the heck is going on here. And this won't be a perfect sketch, okay? I'm not trying to exactly get it. But for x less than negative 2, this function is 9x. So it looks something like that. Some kind of line that ends before we get to negative 2. And then after that, for x greater than or equal to negative 2, this thing is some kind of, I'm trying to get the graph sort of right here. It's some kind of square root function. Looks something like that maybe. And we're looking for x as x approaches 3. You see, I don't care about this thing over here. It's irrelevant. It's like distracting information that doesn't matter in the question. I'm trying to find the limit as x approaches 3. I've only got to use the square root part of this thing. Okay. To be clear, though, there's a whole bunch of functions you don't have to worry about for limits. Polynomials, sine, cosine, all those things are continuous. When you see those things, you just sub in. Even a piecewise, at worst, in a piecewise, you're going to have to sub in twice just to make sure it matches up. So all those types of functions you've seen before are not too dangerous. The ones that are dangerous are the ones that have asymptotes, and actually, subbing into them won't cause you a big problem. You'll just find out it doesn't work. Yeah, you'll sub in. When you sub in, you'll get an error on your calculator. So it's not that dangerous to sub in, except this one. The square root function's the only nightmare in all this thing. And there's a problem with it. I'm going to draw it and then see if someone can tell me what the difficulty is with everything I've set up here. Square root of x minus 5, so it's moved 5 to the right. Here's a sort of good drawing of y equals root x minus 5. And what's the problem with trying to find the limit as x approaches 5? I'll give you a hint. Finding any of the limits over here is no problem. Finding any of the limits over here is also no problem because there's nothing over there. There's no limit that's going to exist over there. But why is 5 a major conceptual problem in the middle of all this? Yeah, we can only come at it from the one side. And the limit definition was very specific. You had to be able to come at it from both sides. So what you can do is this. You can say, okay, limit as x approaches 5 of the positive side of root x minus 5 equals 0. Coming in from the right-hand side is no problem. But coming in from the left-hand side, we have to say does not exist. There's no other choice there but to say does not exist. There's nothing over there. How can it approach anything? How can I come at anything from the left side if there's nothing over there? And so I'm left with the only conclusion possible is that this limit does not exist. That leaves people unhappy about limits because they say, I can see it approaches 0. I'm like, I know, but limits were specific. They had to come at the thing the same from both sides. To be clear about why you have to come from both sides, without just the definition, I promise as the chapter goes along, that'll become clear why it's so important that we get it from both sides. For now, it's like, oh, it's just the definition. You need the same thing from both sides. And this thing doesn't even have both sides to even think about that. Any questions about that scary example? I got to tell you, if I was ever to use this on a test, and I think I did one year, it was an ABC question. It's like question 10. I said, 10, question, part A. Please draw the square root function of x minus 5. Good. Part B. Explain why the limit as x approaches 5 from the positive side is 0. Yeah? Then, part C. Now explain why the limit of x approaches 5 of root x minus 5 cannot exist. Yeah? So it really leads you to it. You know, I'm just going to leave you out in the cold with something like this. Because it's not that important an idea from a day-to-day basis. Yes, we need this information, but it's not vital to every little thing we do in this chapter. Okay? Okay, here we go. This is what I was talking about when I said that you'll know what's coming on this next Chapter 2 test, which we've got a great chance of getting to by the end of the week, by the way. If that freaks you out, that's the way quadmesters is going to work. Yeah? Just think about quadmesters for a second. 5 days, 20 periods, that's 20 classes. You have tests more than every 20 days. In math class, normally every 10 days. So you got to be starting thinking about a test like twice a week. Yeah? The other option available to us, and some university courses will do this, is my last 10 math courses were all 100% final. No assignments, no midterms, no tests, just 100% final. We loved it once we got into it. Once you got the right mentality about it, it made the whole thing a lot easier. Fall a week behind, you're okay. Yeah? Have to spend all your time on your chemistry for a little while? No problem. Get sick? Still a problem. You got to catch up eventually, but you've got all semester to get yourself ready. Yeah, so that was another way to go at it. We're not there yet, but we're on the opposite end where you're getting multiple opportunities, lots of chances to do these tests. Okay. What happens when direct substitution doesn't work? I just want to talk about 0 for a second, because we really got to get 0 down pat now. We're finally going to get to the end of the 0 story, which is a total lie. There's so much to know about 0, it's insane. But there's a problem that's been looming for a long, long time. 0 started off as the easiest number. Way back in grade 6, 7, when you were learning multiplying and division, you knew when 0 came up, it was the easiest question, right? Because 0 times anything was 0. 0 divided by anything is 0. If 0 was in the question, the answer was 0. So that's the first thing I want to write over here. 0 divided by anything is 0. That was your first understanding of 0. But there's a 0 that doesn't come up in any of those little flashcards or in your Mad Minute sheet, and that's when you take anything and divide it by 0. And I tried to talk about this a little bit in advanced functions. And this is the restrictions from grade 11. You can't divide by 0. Not sort of like can't like, oh, it's going to take a new 21st century Einstein, the smartest person we've ever met, and they'll figure out how to divide by 0. No. You cannot divide by 0. You can't take something and divide it into 0 pieces. Take $20 and, okay, make piles of 0. You're like, how do you take $20 and make piles of 0? It's never going to work. Division wasn't designed to divide things into 0 pieces. The whole definition of division is divide it up into pieces. You can't then say 0 pieces. So anything divided by 0, no answer. We say undefined. The reason I'm saying no answer here is because we're going to get a little bit more understanding of what the heck is going on here. Then there's something even worse. It's so much worse we don't really even mention it till right now. What happens if it's 0 divided by 0? Because that's a whole nother ballgame. Shouldn't 0 divided by 0 be something? Like 0 divided by 0, you're dividing something by itself. You'll get a deeper understanding of 0 divided by 0 as we go along. Your first level of understanding for us is there's going to be more work to do. So both these previous situations, 0 divided by anything and anything divided by 0, when you ran into that, that was the end of the question. 0 divided by anything is 0. Anything divided by 0, no answer, and you just stopped. When you run into 0 divided by 0, there's going to be more work to do. And I'm going to explain totally what the heck is going on, why there's more work to do. Using this example right here. Back to tests. You can write it down right now. These things I'm going to do right now, there's going to be a question on each type of these. I usually put it on the first page of the Unit 2 test. There's going to be one where I go, you're going to have to factor this thing to get the answer. This strategy will be called factoring. I've totally given that away. Okay, when you first get this question, though, after what I've taught so far, you're going to be thinking substitution. And substitution is always the way to do limits. So you substitute in, and you go, okay, x approaches 2, I'm going to sub in 2. 2 cubed minus 8 over 2 squared minus 3 times 2 plus 2. I get 0 over 0. And for your purposes this chapter, 0 over 0 means, okay, we got work to do. And the nature of the question is going to tell you what kind of work to do. And I'm going to show you different strategies. First strategy is factoring, because we could factor this thing. So what I'm going to do is try this again and do my factoring before my substitution. I'm going to do the bottom first, just to get you warmed up on factoring. Two things that multiply to positive 2, but add to negative 3. X minus 2, x minus 1. And then, rearing its ugly head, it's back. X cubed minus 8. I believe that was online learning. Difference of cubes. Guaranteed a lot of you just took and when the assignment came up, you looked in the textbook, okay, write this down, okay, done. Yeah? But it's back. Difference of cubes. How do we do difference of cubes? I can hear his brain working. I can feel it up here. Yeah. Now, how do you know if these are plus or minus and everything like that? Well, you need the pattern, or you need a plan for difference of cubes. Maybe you're looking at that going, I don't remember difference of cubes at all. Okay, put that on the shelf, star that and say, by the time I get to the homework for this, I got to get difference of cubes down pat again. Okay? You might want to watch my old video on difference of cubes. You might want to watch a Khan Academy thing on difference of cubes and get that back. But maybe this helps. There was these patterns. Does this ring a bell? And this is like difference of cubes for anybody. That's what I used there. Okay. Now the rest of the big idea here. X minus 2, x minus 2. Those cancel. There's the 0 over 0 part. See, when I subbed in before, I got 0 over 0. Now, I just canceled out the 0 over 0. That's gone now. Now I will be able to substitute into it. And if you think I'm cheating, I can explain away the cheating in just a second. If you think, wait, something's wrong here, I can explain. So I sub in 2 now. 2 squared plus 2 times 2 plus 4 over 2 minus 1. I get 4 and 4, I get 12 over 1. I get 12. Hopefully your brain's exploding. You're like, whoa, what are you doing? Lots of stuff, and I can explain it all. The first thing I need to tell you that might help a lot is that if I were to graph this function it would have a hole at x equals 2. So I don't know exactly what this function looks like. Draw a little picture down here. I don't know what's going on. It does all sorts of weird stuff. Don't care, don't care, don't care. But at x equals 2, this thing heads up to some value, and then there's a hole, and then it carries on from there. Why do I care about that? Okay, when there's a hole there, there's nothing there. So when I subbed in originally, I found out the function goes, no, there's a problem here. But because it was 0 over 0, it's potentially a problem I can make go away. I can't find the value of the function here by direct substitution, but I can find the limit. You see the power of limits. The limits didn't say what is the function. We already had that down pat. We already know how to find what is the function. Limits are, where is it heading towards? It's heading towards 12. And now I can tell you where that hole is. That hole is at 2, 12. We've now found the hole. Do you remember holes in the I tried to tiptoe around it in advanced functions. I'm like, I'll just ask. So and you guys answer, okay, it's a hole. But maybe you didn't really comprehend exactly everything that was going on. And now the circle becomes complete. Literally. That you now see, oh, the limit is where is it headed towards. Now, over here, this said, after you do a cancellation like this, you're supposed to go, comma, x can't equal 2. You say, you just said x can't, I know x can't equal 2, and you just subbed in 2 to that. I'm like, I know. I didn't put in, I put in x equals 2, but I wasn't finding out, I was in a limit, I was finding out where is it headed towards. I didn't make x equals 2 per se. I said, by putting in 2, I can find out where this thing is heading towards. It closes a circle of thinking that started with restrictions back in grade 11, asymptotes and holes in grade 12, and now finally limits closes the whole gap and said there's 2 different ideas going on here. What is the value of the function? We can't find the value of the function. Where is it headed towards? We can factor and cancel and sub in and find where it's headed towards. We can find the limit. Maybe 0 over 0 doesn't mean more work to do. Maybe it means potential hole. And I say potential because there will be questions that come up along the way that still can't be done. There's no amount of techniques that allow you to find the limit, even though it's 0 over 0. Not the ones you're going to see. The ones you're going to see will always have a method to solve. Questions about this? Got to brush up your factoring skills. Got to be able to factor, for sure. Next method. I'm not going to name it yet. I'm just going to go ahead. Say you run into this function some along the way, and you're like, oh, I need to find limit as x approaches 0. Your first move is always substitution. Sub in 0, square root of 0 plus 1 minus 1 over 0. Well, I already know we're in trouble here. 1 minus 1 over 0. 0 over 0. Now let me write the notes under here so you understand where we're at. When you get 0 over 0, 2 things need to happen in your brain. One is there's more work to be done. 2 is this is a potential hole. And why do we care that it's a potential hole? Because even though we can't evaluate where the function is at that point, we might be able to find out where it's headed towards, and that's what limits are. We might be able to, if we have the right strategies available. New strategy coming up here. Oh, you're going to love this one. This is so good. Limit as x approaches 0. Here's my more work. The first time through, I have no idea who came up with this the first time. Because every generation since has had to learn this from somebody else. I don't know how long you'd have to sit there to figure out what is about to happen here or why it works. No, we'll see why it works, but who came up with this first, I don't know. Here's what I'm going to multiply by. Well, okay, let's just talk about multiplying by things. There's only one number you're allowed to multiply things by and not change their value. It's the same number all the time. It's the cutest mathematical trick I know of, is to multiply something by this number. It doesn't change its value, but it changes its form. What number can you multiply by and not change the value? 1. Yeah? And just like life, it's important to choose the right one. And the right one for this question is this guy. And while I'm writing it, you reach back into the recesses of your brain and see if you can remember what that thing is called. It's the conjugate. Powerful weapon. You don't reach out for it very often. By the way, is Fortnite over? Is that fad gone now? Still around? Was there a weapon in Fortnite that only when things were rough you broke it out? You didn't use it very often, just every once in a while. Something's flashing in my brain. One class told me, I've never played Fortnite, but is Legendary Scar, is that a thing? You don't even know. Anyone know about Fortnite? Oh, I see a couple people smiling like, oh yeah. The conjugate is such an important weapon. You don't use it very often. What's the hint that it's coming up? Square roots. When you see square roots, you're like, oh yeah, just a second. Let me get my conjugate. Where did I put it? It's in the drawer here. You know, you break out the conjugate. And here's the beauty of the conjugate. There's square roots in the numerator. Huh? When you go root x plus 1 times root x plus 1, you get x plus 1. When you multiply a square root times itself, it disappears. Then I get, when I'm doing this FOIL on the top, I get a root x plus 1. And at that moment, you lose faith in the conjugate. You're like, now I got a root in there. So I went root x plus 1 times root x plus 1, and I got x plus 1. Then I went root x plus 1 times 1, and I got root x plus 1. And you're like, this is getting worse, Mr. Todd, not better. You know, you're making a big mess here. I'm like, oh, keep going, keep going. Negative 1 times root x plus 1, negative root x plus 1. Now you love the conjugate. Yeah? And then negative 1 times 1 is negative 1. I got to tell you, the conjugate is used for one purpose. To explode its own conjugate. See, these things are conjugates of each other. It's not there to do other stuff. So don't multiply it out with other stuff. Okay? So, a conjugate multiplies with its conjugate. That's what it's for. Don't multiply it with other things. You look at the numerator and you're like, yo, Mr. Todd, all you've got is a big hairy mess there. I'm like, oh yeah, check it out. X, yes, I got X, plus 1, minus 1. You're like, well, isn't that convenient? Yeah, I know. That's what the conjugate is. It's so convenient. It just does exactly what you need to happen. Positive root x plus 1, negative root x plus 1. You're unimpressed. Oh, it gets better. Watch. In the denominator, x, it's x. You're still unimpressed. I've switched colors. What happens with the x's now? They cancel. It's better than that. The 0 over 0 is gone. That took care of the 0 over 0. I can now find out where this thing's headed to by just subbing in. By the way, what's 2 divided by 2? 1. What's 3 divided by 3? 1. X divided by x is 1. So when you cancel those out, we usually just stroke them out because we don't care about them anymore. But if there's nothing left, there's not nothing left. There's 1 left. You know, you're dividing things out. Now we can sub in 1 over root 0 plus 1 equals 1 over root 1 is 1 plus 1 is 2. Lots of stuff here now. We found the limit. We know where this thing's function's headed to. And if this was a hole, we'd know where the hole was. It's at 0, 1/2. There's a hole there. We couldn't find out the value of the function, but we could find out where it was headed towards. Huge applications coming. This strategy is it's just called rationalizing. You did it before and called it rationalizing the denominator. In this particular case, I rationalized the numerator. And there's some problems with that label, naming it that. So I'll also call it conjugate multiplication. That is a better name, but it's not the common name for it. Now, reminder, you only use it when you go 0 over 0. Such a liar. I'm not going to make it. Set the limit at 10:05. Any questions about that example? I'll try and get one more strategy in. Which one is it? Oh, yes. I love this one. But I got to do it fairly quickly. Okay. Rationalizing the denominator works for square roots. It might even work for some other even roots. But generally speaking, that conjugate method will not work on anything above square root. When you get to cubed root, we need a different method. And in fact, this method is so good that if you spend some time learning it, some people, by the time the test comes, don't use conjugate on these ones. They use the method I'm going to show here. So when I put in 0 and I sub it in, I get third root of negative 27 plus 3 over 0, negative 3 plus 3, 0 over 0. Now let's just make sure we're clear on what 0 over 0 means. The first thing it means is there's more work to be done. And by the way, it has a name. It's called indeterminate. It sort of means, well, there might be an answer. I don't know. I can't really determine it yet, but there might be an answer out there. So we know there's more work, and this might be a hole. And why we care that it's a potential hole is that we can't find its value. We've just decided we can't find the value of the function there. There's a hole there, potentially. But maybe we can find the limit. Maybe we can find out where it's heading towards. All right. Another thing you just got to see once. You got to see the whole thing landed to make sense of it. This mess, the cube root of x minus 27. There's no way I can factor and cancel anything, because basically both the previous two methods involved canceling. There's no way I'm going to be canceling things out with that cubed root in there. So I'm going to do a change of variable, it's called. You might not have seen this before. It's an incredible strategy. If you think I'm cheating, then you just quiz me on it along the way, and I'll explain why I'm not cheating. I'm going to try and make this easier by, instead of every time I see cube root of x minus 27, I'm just going to write the letter u. If that feels like cheating, it's okay. I'm going to close all the holes here, all the potential cheating moments in there. After doing that, I'm also going to have to replace this x down there, so I'm going to solve for x in this. So cube root becomes u cubed. I'm going to put that all in a box. I like when little things are like that in a box where you go, okay, here's what I'm going to use now. And now I'm going to rewrite this whole limit using these things. And what's really going on, folks, is that this limit I've been given is just disguising itself. It's disguised as something complicated when it's actually something fairly simple. And we're going to find out how simple it is. So I'll get to this in a minute. It says x approaches 0. I'm switching over to u's. I got to deal with that, and I'll show you how to deal with that in a second. I'm just going to read through this and replace everything that has x's with what I've now called u's. Cube root of x minus 27, I called that u. And x became u cubed plus 27. Do you see what I mean by disguised? That cube root mess made it look like something really complicated was going on. But with a clever change of variables, it's not all that complicated at all. It was something plus 3 over something cubed plus 27. It's just been cleverly disguised. For some reason, something happened there. I'm going to keep going with this, and if you're worried about this, you should be. And I'll get back to it. Okay, I'm just going to leave that for now blank. Because the rest of it is pretty nice. What I mean by pretty nice is little sum of cubes, which again, if the sum of cubes is causing you a headache, why, yeah, you got to brush up on that like soon. 10:05? Oh, I'm going to be really close here. Okay. Now, I changed everything to x's, so this can't be limited as x approaches. Like, when I get to the end here, I can't be subbing in x's, technically. You could technically, now, instead of writing u, you could write this big mess. You could bring it back and just sub your x into it. Technically, you can do that. I don't suggest it. It's a little bit awkward because to figure out what u is not a big problem. If x was supposed to head to 0, so this should be part of the box here, as x goes to 0, u must go to cube root of 0 minus 27, which is negative 3. Yeah? You just take the x value they want to sub in, and you sub it into your u, and you find out what u's got to head towards. So the u in this case was, all along, has to head to negative 3. That's just a straight sub to find out what u value matches up with an x value of 0. Then I can sub this in, and I get 1 over 9 plus 9 plus 9, 1 over 27. That takes some practice. You're going to want that written down, ready to go, and ready for cube root type things. This is called u substitution. But next year it's going to be called change of variable. I didn't get to the last example, and I will, and I'm not sure when. I really hope I'll do the last example after your test this afternoon, because I promised 10:05, and I'm within 45 seconds. Just to be clear, though, the opening questions of the test are, can you factor? Can you rationalize? Can you u substitute? I'm not saying these are easy. I'm just saying you know what's coming. Yeah, it's not like there's no weird prediction here about what's going to be on this test. You already know 3 of the questions that are going to be on the test. Are we clear on what? Any questions about that before I stop the video?